Hi students. So today we start lecture 61 in our course, and today I'm going to finally derive the circular and escape velocity. So these are the particular velocities you need to circle around the earth and to escape the earth and go to some different planet. So these two velocities are going to be derived today with a lot of mathematics in between, but I promise you that at the end of all that math you are going to get a revelation in terms of simple formulas which are going to express the circular and escape velocity. I'm Dr. Ranjan Ganguly. So let us again look at the Earth. We mentioned before that there are essentially two main objectives which you do in terms of design of space vehicles. One is that there are a whole lot of vehicles which tend to revolve around the Earth. So these are placed in circular or elliptical orbits. And these are typically vehicles such as satellites. Satellites form an important part of the entire modern infrastructure. There are weather satellites, there are communication satellites, there are various other kinds of satellites also. Now, beside these satellites, there are also these interplanetary vehicles or vehicles which go to the moon. So essentially, these vehicles take off from the Earth and then they get out of the Earth, they go to the moon, they go to Mars, they go to Saturn, they go to Jupiter, they can go out of the solar system also. So these are the lunar and interplanetary vehicles, and for these vehicles the velocity must be greater than 11.2 kilometer per second to escape the Earth. And if you are going into a circular orbit and want to revolve around the Earth, the velocity has to be 7.9 kilometer per second. So at the end of today's lecture, you are going to exactly know how these two numbers are obtained. So let's start with the orbit equation once again. So recall the orbit equation was given by this r theta in terms of polar coordinates, and this was h square by k square by 1 plus a h square by k square cos theta minus c. And then we made a couple of declarations that p is h square by k square and e is a h square by k square, and after these two substitutions we were able to write the equation r is p by 1 plus e cos theta minus c. And this is the general equation of a conic section in terms of polar coordinates r and theta. Now, you have seen various equations in your life for conic sections. So if you go back to your coordinate geometry books in high school or in college, first year, second year, and so on, you would have seen simple equations in the XY system or the Cartesian coordinate system for conic sections. But here we are using the polar coordinates. Now, typically we saw that given the value of E or the eccentricity of the conic section, you can get a circle, you can get an ellipse, you can get a parabola, you can get a hyperbola. So today we are going to look at the case E is 0, which is the circle, and then E is 1, which is the parabola. So let's start first with recapitulating the circular path where E is 0. If E is 0, the term here involving cos theta minus c, this simply becomes 0, and therefore what happens, we get r equals to p. So that's something you have to keep in mind, that for a circular path r is p or r is h square by k square, because p is h square by k square and therefore r is a constant, and simultaneously because E is 0, then a h square by k square is going to be equal to 0. So what we are going to do is we are going to obtain an expression for E or the eccentricity, and then we are going to set it equal to 0 to obtain the circular velocity. But before we do that, we need to go through a lot of simple algebra and trigonometry and get that particular equation. So let's start with the value of the quantity r. So r is the definition of the conic section here, and we'll start from that, and throughout keep in mind that p is h square by k square. So let's first start to get the value of r dot. Now what we do is we differentiate this r and we immediately get this equation here. So remember, this is in the form u by v, the value for r, and so we can differentiate it. It becomes the quantity here in the denominator, which we see here, into the derivative of p minus the quantity here p into the derivative of the denominator. So That's the use of the formula for derivative of a function of the form u by v. And in the denominator term, you get 1 plus e cos theta minus c, this value square. So using this equation here, we get this equation. Clearly, you can see that I have p dot, the derivative of the numerator here. And in this case, I have 1 plus e cos theta minus c derivative. That would be simply minus e sine theta, theta minus c into theta dot. That's the term which has come here. So you can easily get this equation for r dot. Now immediately we can make a substitution that p dot equal to 0 because p is a constant h square by k square. Remember from the first orbit equation, h square is a constant value, and also k square is simply capital G into capital M, and that's also going to be a constant for a given planet. So once we set p dot equal to 0, I get this simpler equation here. So I only get the term involving pe sine theta minus c theta dot divided by the denominator 1 plus e cos theta minus c square. Now let me take this equation here, and I will immediately realize that I can make a substitution of r is p by 1 plus e cos theta minus c into this equation for r dot. So I substitute r here, so I get rid of one of the p, 1 plus e cos theta minus c, and so I get this equation here. So you see what I've done, I've simply put in an r value here and replaced p by 1 plus e cos theta minus c. Therefore I get an r here. Now I'm going to work further with this r dot value. So remember, r is this equation, r dot is this equation, and therefore I can now get the kinetic energy of the system. Kinetic energy was half m r dot square plus r theta dot square. This we had obtained during the lecture on derivation of the orbit equation. If you did not look at it, go back a few slides and take a look at that. So this I can write as half m, and then I get r dot square and r theta dot square. So r dot square would be simply the square of this term, which is this term here, and then the second term is going to be r square theta dot square. So this is the kinetic energy of the system, and as you would expect, it depends on theta dot square. It also depends on m, and there are some values of r square also thrown into this equation here. Now I just rewrite that equation here for convenience, and then I'm going to make another substitution. The substitution involves the fact that h is r square theta dot. Remember, h is the angular momentum per unit mass. So this was the definition from again the lecture where I derived the orbit equation. So from this equation I get theta dot square is going to be h square by r4. So I've simply taken theta dot from this equation and squared it. Now theta dot square is present in this equation at two places here, and so I'm going to make a substitution here. So I make the substitution here, so I get h square by r4 and into r square. So I get h square by r square. That's the term we get here. And in this case, what happens? I replace theta dot square by h square by r4. And therefore, I'm going to get the h squared term here. And then remember, there was r square here. So I get a r square term here because there is a cancellation of r square and r4. And so I'm left with r square. So this is the equation I get when I substitute h is r squared theta dot into this equation. All I have done is I have got rid of the theta dot term and I have replaced it with a term involving h and r. So let's again rewrite that last term here, and now I'm going to make one more substitution. We are going to use the equation here for the conic section, and we are going to rewrite it because we know p is h square by k square. So I can write r 1 plus e cos theta minus c, that's this term here, equals h square by k square. And when I do that, I get this equation for t from this equation here. So all I have done here is I have taken this value you see in the denominator and I have applied this equation here. So this equation squared would give us h4 by k4. So you see here h4 has come, here k4 has come, and so that is the equation here. This equation h square by r square remains exactly the same. Now in the next slide, I'm going to simplify this equation by cancelling h square with h4 and then further work on that. So here I have written that equation again. Now I have the h squared term here. And so I'm going to take this equation and I'm going to slightly modify it again. So I'm going to use the fact the conic section tells me this equation here. And so what I'm going to do, I'm going to take this equation and substitute it here. So to make that substitution, I can clearly see that this equation, if I pull out k4 and h square, I get this equation here. So all I have done is pulled out k square and h square. I got these two out here. So here I would have to multiply by h square to get h4, because h4 into h square would give me h square. And here I have divided by k4, so that k4 into k4 gives me the value 1. So with this slight modification, then I expand this equation out here. So here what I have done is I have replaced the h4 by k4 term by r 1 plus e cos theta minus c square. So this is where the substitution is made from this equation here. And once I substitute h square by k square from this equation here, I get this equation. Now what I do is I expand this part here, that is 1 plus e cos theta minus c square. Now remember the formula of a plus b square is a square plus b square plus 2ab. So I get 1, that's the a squared term. The b squared term is e square cos square theta minus c, and the 2ab term gives me 2e cos theta minus c. So I get this equation here, and then what I do, I look at both these two equations here, and then I immediately use the fact from trigonometry that sine square theta minus c plus cos square theta minus c is simply 1. So I get one term involving just e square, then I get a term involving 1, and I get the term 2e cos theta minus c. So this is one place where we are using the very simple relation from trigonometry, that sine square x plus cos square x equals 1. So I get this equation for t now, and this you can see has been simplified considerably from what we started with. Now we are going to take this t equation and we are going to let it be here right now. Next thing is we are going to look at the potential energy part, because we are planning to calculate the Lagrangian H. So let's start with the potential energy, and we are going to take the modulus of that. So we'll take Gmm by R. This is k square m by r. So remember, k square is capital G into m. Now this becomes m k4 by h square into this, where I have made a substitution essentially from this equation here. So I have taken the value of r and I have substituted into k square by m. So r would be h square by k square into this 1 plus e cos theta minus c term, and that substitution has been made here, and I have got this equation. I have got rid of the r. So the whole aim here was to get expressions for t and phi such that it's only dependent on one variable theta. We have got rid of the r from this particular expressions, or these particular expressions. So now let's rewrite phi slightly so that we get the term outside, which is very similar to the t term. So I got half m k4 by h square here, and so what I had to do, I multiplied this by 2 here, so that 2 cancel out, and again I multiplied this term by 2 here. Now what this lets me do is that it lets me very quickly calculate h is t minus mod phi, and this is going to be half m k4 by h square, and then I simply have to add these two terms. So 1 and 2, if I subtract these two, I will get minus 1. This one simply cancels out, and this one gives me plus e square. So I get h is half m k4 by h square bracket minus 1 plus e square. That's the expression for the Lagrangian. Let's move forward now. I wrote that h here now, and I have adjusted it slightly so that I brought the negative sign out and I wrote it in this manner. So h is minus half m k4 by h square 1 minus e square. Now what I do is I take all these terms to the left hand side, so I can write this expression here, and on the right side I am left with minus 1 plus E square. So once I get this, I can very easily get the expression for E is root 1 plus 2h square h by mk4. So this is the equation we were aspiring for a long time. What I had mentioned, we need to get an expression for E, because then we are going to be able to set E to 0 to get the circular velocity and E to 1 to get the parabolic velocity. And so now I have this in terms of small h, capital H, m and k. So let's start with the circular velocity. To do that, I take the value for E, or the expression for E, and I set it equal to 0, because E equal to 0 for circular velocity. As soon as I set it equal to 0, I can simplify it slightly and I can write h as this expression negative mk4 by 2h square. I then keep in mind the fact that h was t minus v mod, and therefore it was half mv square minus gmm by r, and therefore I can take this equation and I can equate it to the h I calculated before from those expressions. So that gives me this value here. So now I have these two equations. I can write it in this form. So I get a reasonably compact equation relating the kinetic energy part with the part coming from the potential factors in the system. So now I'm going to take this equation and I'm going to simplify it further. But before that, we keep in mind that when you are considering E to be 0, then R is going to be P, because E is going to be 0. So R is going to become equal to P divided by 1, which is P. Also E is 0 and P is of course defined as h squared by k square. So I can write then h square is pk square or h square is rk square. That's the equation I'm getting by combining these two equations here. And also remember k square is gm. Now again, rewriting the equation we got in the previous lecture, I get this equation here, and then I can write this equation in this form. So what I've done is I've taken g capital M, replaced it by k square, and got this equation here. And another thing I've done is I have replaced h square by rk square. So that has given me this r here, and k4 has become k square because of cancellations. Now further simplification is going to give me half mv square equals mk square by 2r, and at this point the m cancels out, which is the mass of the spacecraft, and I get v is root k square by r. So this simple formula, like I mentioned before, is the formula for circular velocity, and this gives us the velocity at which we should be if we want to circle the earth. So v is root k square by r, very important formula, tells you the circular velocity of the system. And now if we put the parameter for earth, which is k square is gm, is 3.956 into 10 to the power 14 meter cube per second square, then we are going to get the value of v corresponding to earth. Also remember the radius of the earth is 6.4 into 10 to the power 6 meters. So we substitute these two values here. These are all physical quantities, and I get the circular velocity here. Note these things are going to be different if I'm on a different planet. The values of g, m and r are going to be different, so the circular velocity is going to be different. The next equation we are going to get is the escape velocity, sometime also known as the parabolic velocity. So again, we start with the general equation for E I derived before, and we substitute E is 1 now, which corresponds to the trajectory of a parabola. So I put this here. This equation is even simpler than the one previously, because I immediately get, I can square both sides and then the ones cancel out. So I get 2h square h by mk square is 0, which can happen if capital H is 0 or the Lagrangian is 0. Now I get the Lagrangian T minus mod phi, that is half mv square minus gmm by r, and this will be 0. So from this equation I can immediately write that v square is 2g capital M by r, or 2k square by r, and I immediately get v is root 2k square by r. This thing in yellow is the parabolic velocity or the escape velocity if you want to escape in the trajectory of the parabola. So this is again an extremely important relation which you should commit to your memory, that v is root 2k square by r, and though the derivation was difficult, it involved a lot of theory about conic sections, about trigonometry. We see that at the end of the day we got very nice compact equations. So if people tell you that conic sections are not required, coordinate geometry is not required, trigonometry is not required in high school, keep in mind that without these you cannot learn the basics of rocket science which you are learning today. So we take k square here and we substitute it in this equation along with r, and we get the escape velocity to be 11.2 kilometer per second for the earth. So what this tells us is that if at burnout Vb is greater than 11.2 kilometer per second, the vehicle will escape the earth in a parabolic trajectory. So to summarize, we did a lot of math today. We looked at the orbit equation. We used it to get an expression for E. And after getting the expression for E, we set it to 0 to get the circular velocity. We set it to 1 to get the escape velocity. And you can clearly see the circular velocity and the escape velocity will be related for a given planet. There is a factor of root 2 between them. But these are completely dependent on k square, which is g into m, and r, which is the radius of the planet concerned. So for earth we calculated the values here. You can find various values of different planets such as Mars, Jupiter and so on from Google, and then you can calculate the circular velocity and escape velocity corresponding to those planets also. So today's lecture introduces you to some basic thought process behind orbital mechanics, between space mechanics, between the mechanics of a spacecraft, which is required whether you want to launch a satellite in space, then you need the circular velocity, or you want to get out in space and explore the final frontiers like a Star Trek explorer. So I hope you enjoyed this video, and in the next lecture I'm going to start looking at Kepler's laws. So those are going to tell us about the laws regarding satellites which are orbiting around a planet such as the Earth. So Kepler laws are very important because we have a lot of satellites out there in space. We now have thousands of satellites. Not only these satellites are in the higher regions, for example the geostationary, but also in the LEO regions, and these satellites are often being used for telecommunication, even for internet, for navigation in the seas, for Google Maps, for Apple Maps, and so on. And there are actually satellite systems by different countries. So the US has the GPS system, the Russians have a GLONASS system, and so on. And so depending on whichever system you want, you have to use that. But do remember that satellites are a very important part of the global communication system. I would suggest that you do some problems from Anderson's book to cement the concept, which we are following as the textbook here, and that will certainly help you to get some physical feel of the numbers involved in using these equations, because that's going to be very important for you if you ever take up a job in some firm which deals with space related applications. So I'll end my video now and I will see you in a lecture sometime soon. See you then.